Okay, ladies and gentlemen, we're going to be talking about functions. But since we're talking about functions, here's an awesome remake of an old classic.
Norfolk Southern, what's your function?
Hooking up the country, helping business run. Hey! They haul everything safely and on time. They connect the factories built along the lines. We've got the goods to help give this economy a spark. Our trains, tracks, and bridges, oh, they'll get you pretty far.
Norfolk Southern, what's your function?
Hooking up the country, helping business run.
Norfolk Southern has a function.
Helping this big country move ahead as fun. We're investing.
Okay, ladies and gentlemen. And there is no way I am not putting a link to that YouTube video in the module somewhere. So you can find that later if you wish. Little Schoolhouse Rock to get things started off right. With that, we want to go ahead and start looking at actual mathematical functions. Now, mathematical functions, function notation, because we're creative, we use f of x. F is the name of the function, x is the variable that we're going to be using inside the function, so the function I've chosen is x squared plus 1. Now, of course, anytime you have an equation, you can also have a graph. Anytime you have a graph, you can have a t-table. So we're going to look at it numerically, graphically, and symbolically. Now, in this case, obviously what we can do is fill in our t-table by simply plugging in values, -2, -1, 0, 1, 2. It's your classic set of values. Well, the way you do that is if I said f of -3, you'll notice instead of x, which is sitting in the function, since I have -3, I put -3 in the function. So -3 squared, of course, is 9. 9 plus 1 is 10. So we could put that in right up here, -3 comma 10. We could go graph it. 1, 2, 3, up 10. Back 2, up 5. Back 1, up 2. Over none, here's 0. And you can do the same thing moving up the other side. And with that, you can graph your function. Now, the definition of function, of course, is for every x, there is one and only one y, which means every time I put in a -3, I'm going to get a 10. Every time I put in -2, I'm going to get a 5. Every time I put in a -1, I get a 2. There's never going to be any ambiguity about if I put something in for x, that particular x will give me a certain particular y every single time. Now, we can also use function notation to do other things. And if I had f of 7, I would simply plug in 7 squared plus 1. If I put in f of b, I could do the same thing, and it's going to be b squared plus 1. If I put in x minus 4, I'm going to say the same equation except wherever x was, so something squared plus 1, that's the formula. That's the form of this, except now instead of putting in 7 or putting in b, I put in x minus 4. Now, we already should know from our Algebra 2 days what a minus 4 in with the x should be doing to this. In fact, what it's going to do is it's going to take this function that was a simple parabola that was moved up 1 unit, and now it's going to move it forward 4 units. And so now it's going to be over 4 up 1. Over 4 up 1. That's something you should be able to do now that you've gone through Algebra 2 without use of a calculator. Again, I could look at it numerically by plugging in, but we don't need to. There's the function, there's the graph, it all works together. Now, in all functions, they have the values that form the x's. These are the independent variable, and they're independent because we chose them. Therefore, these are dependent. We also call this the domain. This we would call the range. So the domain is the active component in the x. The range is where it goes from the domain. So independent, dependent, domain, range. Now, another way we can tell that something is a function besides the fact that for every element of the domain there is one and only one element of the range, or for every independent variable there is one and only one dependent variable, is graphically we can use a test. If we use the vertical line test, I can draw vertical lines anywhere in that function, and if they only cross the graph in one spot, the graph remains a function. So in these two cases, we certainly have functions because they pass the vertical line test. So you can think about it numerically, is it a function, or graphically, is it a function? Symbolically, unfortunately, you cannot necessarily tell whether it is or is not a function. There is not a test for that at this point. Now, we could take any number of graphs and say, is that a function? We could say, is y equals square root of x? Is it a function? Now, we have no trouble here. Vertical line test, okay, function. The problem is the square root of x is really an incomplete graph. We have y equals x squared. That looks like this. If x were to equal y squared, and then we square root both sides, y equals square root of x, that would technically give us a graph that looks like this. However, this is definitively not a function. It crosses in two places, in many places. So, just like everything else in upper level math, when we run into something that's a particular problem and we don't want it to be a problem, math people just make stuff up. They absolutely just ignore the lower half of the square root, because as we're well aware of, the square root of 4 is equal to plus or minus 2. Well, the math people say, well, fine, but to make it a function, let's just use the positive portion. And so y equals square root of x looks like this. Now it passes the vertical line test. With that, we now need to deal with piecewise functions. Well, a piecewise function could be something like this. X plus 1 and x squared. With that, where x is greater than, x is less than 0, this is where x is greater than or equal to 0. So if I were to go and graph this, I would say for everywhere less than 0, which would be this portion of the graph, I'm using the graph y equals x plus 1. So we go up 1 unit, up 1 over 1, up 1 over 1, back 1, down 1, and we would have this. The problem is I only want it less than 0, so when I get to here, I must stop. And in fact, because 0 is not included, I use an open circle. Now, where x is greater than 0, it's x squared. Well, that's easy. We'd have a parabola. Except that it's only good when x is greater than or equal to 0. So a solid dot at 0, bringing it up here. You'll notice the graph is not continuous. The graph comes up, jumps down, and continues. But it still passes the vertical line test. And that's why you have to have the open circle and the closed circle, because it's only going to touch in one spot. Now, if I were to say f of 3, I would need to say, well, where is 3? 3 is in the greater than 0 pile, so I would say 3 squared. I would use the x squared component. If f is negative 5, I would actually have to use this pit up here because x is less than 0, negative 5 less than 0. Negative 5 plus 1, the answer is negative 4. So where you plug it into a piecewise function is determined by the domains. The last bit of pieces of domain is as follows. We already discussed that the domain is all the possible x values. Well, that's okay for something like this. It's okay for something like this. We have any x value we want. However, in this case, we cannot use an x value that's negative. If I attempt to put a negative 4 in here, that's going to make this graph way back here. That isn't a real value. There is no graph over the top of negative 4. That also happens when we have something like this, f of x equals 1 over x minus 4. In this case, when we attempt to graph this, 1, 2, 3, 4, we end up with this graph here. I could put in -2 to my heart's content. No big deal. There it is. I could put in +7 if I wished. That's no big deal. But if I attempted to put in 4, I would come up with 1 over 0. And of course, 1 over 0 is absolutely undefined. With 1 over 0 being undefined, that's where we get an asymptote. So we would say the domain of the function is the set of all x's, such that x cannot equal 4. And so we'd say it's the set of all x's such that x cannot equal 4. It could equal any of the other real numbers, but not 4. Most of the time we're just going to say x can't equal 4. We'd say real numbers, x can't equal 4. If we have a square root, let's say we have f of x equals 3 square root 2x minus 1. We say, well, whatever's under here can't be negative, so we would say 2x minus 1 has to be greater than or equal to 0, and begin solving. 2x greater than or equal to 1, x has to be greater than or equal to 1/2, and that's going to be our domain. All right, so with all of that, we need to make sure we send this module out with a bang.
To keep our country in the lead, we keep moving to deliver what you need, and that means jobs. Lots of people making lots and lots of things. Let's get your business rolling now. Everybody sing.
Norfolk Southern, what's your function?
Hooking up the country, helping business run.
Norfolk Southern has a function.
Helping this big country move ahead as one.
And there's your homework for this section. Pause it, copy it, or print it.